For our first talk this afternoon, we have the last talk in Jared Weinstein's
It's not
series.
the last. Oh yeah, in the series.
Yeah, in Jared Weinstein's series, not the last talk of the afternoon. This talk will be on formal vector spaces.
Thank you. So Frank will be giving an extra talk after mine, but we arranged it. I may need to go over by like 5 minutes. I'm going to like borrow 5 minutes of Frank's extra talk. Maybe. Okay. So I've talked to you about p-divisible groups, and I've talked to you about formal groups. And, and when you learn about groups, before you learn about groups, you learn about vector spaces. So actually, this is a bit out of order. But the title is Formal Vector Spaces. Okay. And I just want to set up some pieces of notation. I'm always going to be using the same symbols for various rings. And I just want to let you know so that I can be consistent about everything. I'm always going to use the letter A to be an adic ZP algebra. I'm going to remind you about this. So adic ZP algebra. And this means that A is complete and separated with respect to the topology induced by some ideal I. And also that A is a ZP algebra. But more than that, P is small in ZP. So P should be also small in A, and this means that without loss of generality, I can just assume that P lives in the ideal of definition for A, and I always will make that assumption. Great. So, and A will often be used as the base ring for whatever our investigations are. And sometimes there will be like functors coming out of the category adic A of adic A algebras. And when I want to refer to an object in adic A, I'm always going to use the letter R. R will be a test object. And R will be, of course, separated and complete for the topology induced by some ideal of definition J. And, since the ideal I is small in A, the ideal I should be small in R, and I can always assume that the extension of I to R is contained in J without loss of generality. So that's the setup. A is our base ring. Its ideal of definition is I. R is our test object. Its ideal of definition is J, and I is contained in J. So all of those things are going to be in effect for the entire talk. Okay. All right, so last time when we talked about formal groups, we talked about a certain functor, nil. Nil goes from adic A to pointed sets. And what it does is quite simple. It just takes R, a test object, to nil R, and that is defined as the set of topologically nilpotent elements, the things which are small, and that is really the same thing as the radical ideal of J, J being the ideal of definition of R. Everything that goes to 0 when you raise it to high enough powers. So this thing is representable. It is representable by the formal power series ring A double brackets T, right? Right, because homomorphisms from this guy into R, which are continuous, have to take T to something topologically nilpotent, so you have to land in here. Great. All right, so in today's talk, it's going to focus on a little variation on this, where we do this thing with inverse limits. So I'm going to define a funny sort of functor, nil flat. That's a flat. And nil flat also goes from adic A to pointed sets, and it takes R to, guess what, inverse limit of nil R under the maps x goes to x to the p. Okay. So it's this inverse limit game again. So an element of nil flat of R is going to be a sequence of topologically nilpotent elements. Each one is the pth power of the last. So it's a sequence. This functor is also representable. I mean, all this stuff is formal. I mean, if the original guy was representable by A double brackets T, then this guy should be representable not by an inverse limit, but by a forward limit. So I'll start writing this thing. Limit, forward limit, A double brackets T, along the maps T goes to T to the P, except actually this is false as written. This forward limit is not complete. And if I'm going to claim this thing is representable, it should be representable by an object that actually belongs to there, which means it has to be complete. So all I do is just complete it. I complete it with respect to the topology induced by the ideal generated by both I and T. That's an I and that's a T. Okay, right. And this thing I will define the notation A double brackets T 1 over P to the infinity. Okay. And it's this funny sort of ring that I did talk about at the first lecture. But I do want to remind you of some of its properties and what is legal in it and what is not. So as an example, it might be a good idea to consider the ring ZP double brackets T to the 1 over P infinity. What is an element of this ring? So an element of this ring, well, it's a funny sort of power series. Sum C alpha T to the alpha, and alpha is allowed to have a denominator of P. So it belongs to Z 1 over P, but of course it has to be positive. But there's a restriction here. I mean, the thing is supposed to converge inside of this ring, and that means that as alpha gets larger, you really have to start entering into higher powers of the ideal I, comma, T. In this context, this means that, well, I'll write it out for you. The condition is this. For all n, I can consider the set of indices alpha bounded by n such that the p-adic valuation of C alpha is also less than or equal to n. Okay. This thing I want to be finite for all n. And, well, my eyes glaze over looking at that definition. It's much more instructive to list some examples of power series in this ring. So for instance, this power series. Oh, actually, something rather more fundamental. This power series, all right. Nothing wrong with that, okay. Next would be this power series. So, right, this converges t-adically. So in particular, it converges I, comma, t-adically, or p, comma, t-adically. This power series is a little strange. So that's a p squared, 1 over t to the 1 over p squared plus dot, dot, dot. Okay, so this time I'm not even writing the exponents in the correct order, and I can't because those exponents are not well ordered. So it's a funny sort of series. Nonetheless, the powers of p belonging to these, the coefficients are going to 0, so this is perfectly legitimate. And here's a non-example. I'm not allowed to do t plus t to the 1 plus 1 over p plus t to the 1 plus 1 over p plus 1 over p squared. In this case, the exponents of t are increasing, but they're bounded, and that's not going to work. You're not going to enter all powers of this, the ideal of definition of this ring this way. So this is not allowed. So this just give you a sense of what's in this ring and what's not in this ring. Okay. All right, good. All right, so we've got this functor nil flat. It's always representable by this funny ring of fractional power series. All right, so key to all of the investigations that follow is the following very important lemma. It's rather miraculous, so I suggest kind of thinking about the proof at least once. So it's like this. For any test object R, you know what, I'm just going to write since the notation is so important throughout the entire talk, I'm just going to write it once again. A is an adic ZP algebra, and R is an adic A algebra. Okay. That's kind of how it is the whole time. Nil flat of R, well, this is a functor, so of course, oh, yeah, okay, right. Yeah, I ruined the surprise. All right, nil. All right, so I is the ideal of definition of A. And this is a bit of abusive notation. I mean R modulo IR, the extension of I to R. So when you mod out by the ideal of definition of A, of course there's this reduction map. And it seems to be rather lossy. Like, things in every I go to 0. Nonetheless, this is an isomorphism. Okay, so let me give you a little remark here. This is related to the following phenomenon, where I'm going to be very specific about the objects involved. You can take the ring of integers in CP. You can take OCP and take the same sort of inverse limit and map it to this guy, inverse limit of OCP mod P, and this is an isomorphism. And this is a familiar fact to those who study p-adic Hodge theory. Constructions like this come up all the time. And this lemma is not quite the same as this. This is not quite an application of this, but it is when you say, like, okay, the nil of OCP is this guy, the nil of this guy is this guy, and then it really is an example of this isomorphism. And why is it an isomorphism? Certainly it's not when you erase the flats on either side. Well, what I'm going to do is actually sketch this out for you. I'm going to write the inverse map. We have to start with an element here and get something in here, somehow lift it back in a unambiguous way. All right, it follows this procedure. So let's suppose we start with an element in the object on the right, nil flat of R mod I. So each guy is the p-th power of the one before it, or the one after it, excuse me. And what I'm going to do is just, I want some elements in R, so I'm just going to start lifting them haphazardly. So this arrow is lift, and now I get Y's. And I get a sequence of elements, and they live in R. In fact, they live in nil R. There we go. But they don't live in they don't constitute an element of nil flat because I lifted them haphazardly. This guy to the p is congruent to this guy mod I, but they're not equal. Okay. So I'm going to take this sequence of elements and apply this kind of smoothing operation. So I lift and then I smooth, and I get this. So I'll explain in a moment what I mean. Nil flat R. And I have to define what Zi is. So Zi is the following limit. So since I'm applying a limit, it is so utterly important that my rings be complete, but they are because they are adic rings. So limit as n goes to infinity of y I plus n to the p to the n. I think that's it. Okay. So that's a procedure for constructing the inverse. You have to check the following things. One, that this converges. And the key fact there would be that these guys are p-th power compatible modulo I. Not just that it converges, but it's independent of the lift. Right? I mean, you don't want it to depend on the choice of y's. You've got to check that these zi's are compatible. That is, that they really do constitute an element of nil flat, but that one you can I it, because if you take the zi to the p-th power, that's like turning that n into an n plus 1, do the change of variable, and that decreases the I by 1, so you get zi minus 1. Okay. And then you also have to show that this procedure gives you a two-sided inverse to the map, to the reduction map here. But none of those steps is particularly hard, so I really recommend checking all of this stuff. Okay, so that's the really important lemma from which basically everything in the rest of the talk is going to flow. I call this the crystalline property of nil flat. Okay, of nil flat. All right. So what's next? So I haven't yet talked about any sort of group structure. So I guess the next segment here is going to be called the universal cover of a p-divisible group. Although I'll really just be sticking to the case of p-divisible formal groups. Okay. All right, so first, some abstract setup. So let's say G is any abelian group whatsoever. Let's let, all right, so this notation is just, I'm just going to write a tilde over it, but it's going to mean this very specific thing. I mean, so the prime p is fixed. It's just not notated here, but that prime p is in the background. So I'm just going to take the inverse limit of G under the raising to the p power map inside of the group G. This is something you can do for any abelian group whatsoever. You get a new group. In fact, this group has a special property that you can divide by p. So if an abelian group is a Z module, this is a Z1 over p module. Because, 1 over p, this guy, I guess I'm confusing additive and multiplicative notations, but I think you know what I mean. That just shifts everything over by 1. Yeah. And this is a funny sort of thing. I'd better work out a few examples, but you can do it with any abelian group, like with Z, but that's sort of disastrous because you get 0, because there's no way you can set up a p-compatible sequence of integers, because no integer is infinitely divisible by p. That just doesn't happen. You're only going to get something non-zero if your group has lots of p-divisible elements. For instance, the group QP, well, you just get QP. I mean, multiplication by p is an isomorphism on QP, so this procedure doesn't do anything. More interesting is the case of QP modulo ZP, and a fun exercise is to show that this operation applied to QP mod ZP sort of unwinds the torsion, and you get QP. Yep. And then the example I gave in the first lecture is this very weird thing. When you take the circle, and you get this very strange topological group, R cross ZP modulo Z, the solenoid. All right, so very strange objects can result when you do this operation. Okay. Right. So I'm going to take, this is just sort of the abstract setup. What I'd like to do is apply this in the setting where G is not an abstract group, but rather a p-divisible formal group. All right. On to the next thing. So, same setup with the A and the R. Let's let G over A be a p-divisible formal group. P-divisible formal group. And you've got this operation of multiplication by p in G. So this, of course, just means add x to itself with the addition law in G, do it p times. And when you do this, you get px plus higher order terms. This is a power series in A double brackets x. And our assumption is still in effect that p is small in A. P is topologically nilpotent in A. So multiplying by p in the formal group kind of makes you smaller. And x was topologically nilpotent to begin with. All these other terms are yet smaller. They're like x squared, x cubed. So multiplication by p makes you smaller. And this suggests that the group G of R, for any test object R, isn't just an abelian group, but it is also a ZP module. This is a very important observation. So it's like, let's suppose I wanted to multiply within G by some element of ZP, some power series in P, right? Well, that sort of thing converges just because of this property. And you can check that, but I think it's more helpful to offer an example. The example I want to give is the formal multiplicative group over ZP. This is a priori just a formal group, but it's a fortiori a formal ZP module. So why is that so? It's like for any A and ZP, I have to tell you how to multiply within the formal group like so. So now I'm expecting some power series, And that power series really ought to be 1 plus t to the power of a minus 1, but a is in ZP. But not to fear, this makes perfect sense. This is just some, oh god, t's, fine. This is sum, and at least 1, of a choose n, t to the n, and this makes perfect sense because a choose n is always a p-adic integer if a is in ZP. All right, so this is fine. So things that were a priori just formal groups end up being formal ZP modules over such rings A. Okay. And, oh yeah, right, so I can set up a little diagram of functors like this. So no matter what G is, it gives me a functor from adic A algebras, R, to, well, before, in the last lecture, I would have put abelian groups here, but now I'm going to put ZP modules. Mod ZP, the category of ZP modules. And I had this sort of diagram before, mod ZP. I can forget about the ZP module structure and only remember the underlying pointed set. And when I compose those two functors, the resulting functor is isomorphic to nil, right? So G is this functor. It's representable, when you forget about the group structure, by a formal power series ring, right? That was like this kind of alternate conception of a formal group G. All right, great. So yeah, so this is a formal ZP module, and now I'll tell you about a formal vector space, a formal QP vector space. So here's the thing I define. Oh, that's no good. So let me define a new functor called G tilde, the universal cover. It goes from adic A algebras to vector spaces over QP. QP vector spaces. And R goes to, well, G tilde of R is defined as this same inverse limit. G of R, right? Same sort of thing, except keep in mind that this P represents multiplication in P. That is, multiplication in G by P. So, yeah, so this is this perfectly well-defined thing to do. I mean, I could have also written this as just G of R, the abstract group, tilde. And, all right, so this is a funny thing to be doing, but in the end, you get a QP vector space, right? When you do this inverse limit, P becomes invertible. So it's a ZP module on which P is invertible. It's a QP vector space. And I'd better kind of offer you an example of this thing right away in the simplest possible case. And that case is where A, you know, A is generally a ZP, an adic ZP algebra, but one of those is certainly FP bar. FP bar, right? And let's let G, the formal P divisible group, be, well, why don't we let it be the multiplicative group? Or if you like, it can be the formal group attached to a super singular elliptic curve. I want to get in the habit of writing a 0 there if it's over FP. So here, E0 over FP bar is meant to be a super singular elliptic curve. Then let's examine what multiplication by P in G is. So in the multiplicative group case, multiplication by P is like 1 plus T to the power P minus 1, but we're in mod P, so those 1's go away and you just get T to the P. In the case of the super singular elliptic curve and its formal group, well, you get some power series starting with T to the P squared, but if you do some change of variables, and you can do that because we're over FP bar, it turns out, you can just assume it's T to the P squared, stop, full stop, okay? Or you can imagine some other formal group of height P to the H, sorry, of height H, where multiplication by P would be T to the P to the H. Since we're over FP bar, we can actually always arrange things so that multiplication by P is just raising to a power of T. The addition law, no comment on that. I mean, in this case, the addition law might be rather complicated. I can't write it down. But multiplication by p can be assumed to be rather simple. So in this situation, why don't I look at g tilde of R, a test object? R is going to be just some adic FP bar algebra. And you know, if I forget about the vector space structure, then you know, g tilde is just the same as nil of R, and multiplication by p is just x goes to x to the p, or x to the p squared, or x to the p to the h, but that inverse limit is just, I might as well just replace it with x to the p, okay? So great, we get this. Oh yeah, but we already defined this, it's just nil flat. So it's nil flat of R. So g tilde of R, once I forget the vector space structure, is just nil flat, and that means I can set up this commutative diagram. So adic A, here's g tilde, here's vect qp, here's pointed sets, and this guy is just nil flat. Great. So this is the setup. It's a functor from adic A to qp vector spaces such that the underlying set is just this nil flat functor. And any functor G that satisfies this, I call it a formal qp vector space. Although sometimes I don't say the qp part. Okay. Rather than a formal group or a formal ZP module, it's a formal qp vector space. Great. All right, so that was the simplest case when A was just FP bar. What about more interesting rings, like in characteristic 0? So I'm going to just make a, yeah, it tends to bleed through. I'm just going to make a mild assumption. Next case. And this is the assumption that A modulo its ideal of definition is FP bar. That is, A has an ideal of definition whose quotient is FP bar. And obviously the thing I want you to think about is W of FP bar. So, e.g. that guy. Yeah. You know, that's a DVR, right? So that's helpful. And let's say we have given a formal P divisible group G over A. You know, think about that supersingular elliptic curve again. Or the multiplicative group, whatever. And I want to get in the habit of writing G sub 0 for objects over FP bar, things that want to be deformed. So I'll just do this. That's going to be the exchange. Okay. All right, great. Then here's the thing. For our test object in adic A, we have a map from G tilde of R, the kind of mysterious thing that was defined as this inverse limit, to, okay, I can just take G tilde, I can just reduce everything mod I. But mod I might as well put a 0 here, right? Because mod I, this is just the base change of G to FP bar. This is just, you know, FP bar is just A mod I. So it just really only depends on G0. And guess what? This is an isomorphism too. Okay. Yeah. And this is, yeah, rather a surprising statement. But the principle of its proof, is exactly the same as what I did for the functor nil flat. To go the other direction, you take a compatible sequence here, lift it haphazardly, and then smooth. The result converges, and you get the inverse map. So it's something that only seems to happen with the universal cover G tilde. Obviously, it does not happen with G. Okay. Great. And so this means that if I forget about the vector space structure, well, I just pass this isomorphism like so. But the thing that I just did about G0 is I showed that this was the same as nil flat of the test object, R mod I. But then I can appeal to the crystalline nature of nil flat and find that this is just famous nil flat of R. So I kind of Started at R, went down, went over, and went up again. And this means that, looking over here, I can really set up the same diagram with A. Yeah, right. I mean, G tilde composed with forgetful is nil flat, and therefore by my rather ad hoc definition, G tilde is a formal vector space. To space over A. I guess that's rather confusing. I should maybe keep writing the thing. Let's not confuse. It's a vector space sort of with multiplication by QP, but the base ring is A. Okay. Yeah. All right. So as a corollary of this, we have the following very surprising properties. So we've been studying the deformation theory of p-divisible groups. You got something that starts off in FP bar, and we wonder how to lift it to characteristic 0. And there's often many ways to lift a p-divisible group, uncountably many ways. But here's the thing. If G and G prime are two lifts of G0 to A, so remember G0 is this thing over FP bar, and let's suppose I'm given two lifts of it up to A. Then G tilde evaluated on a test object is the same as G naught tilde of R mod I. But of course that's the same as G prime of R, because I am applying this thing to both G and G tilde. So I get the same thing in the end. And this means that, tilde. And this means that G tilde is isomorphic to G tilde prime. Okay. So even though formal groups, there's uncountably many ways to lift a formal group from FP bar to the ring of bit vectors. But there's only one way to lift to a formal vector space over the bit vector set. So formal vector spaces have this amazing property that they lift uniquely. Their deformation theory is always trivial. So that's incredibly helpful. All right. All right, so we're just kind of developing a theory of formal vector spaces, and I like to call that theory formal linear algebra. So this has like two headings, I guess. One of them is that I'm curious about what multiplication by p does in the formal vector space. So let me leave this assumption in effect. So we keep the assumption that A mod I is FP bar. So that worked out pretty well for us before. And we have our guy G0 over FP bar. And let's have some lift of it, G over A. So these are p-divisible formal groups. Now, multiplication by p in G0 is very simple. After a change of variable, maybe, it's like t to the p to the h, where h is the height. So for the multiplicative group, it's height 1. For that supersingular elliptic curve, it's height 2. There's one of every height. But multiplication by p in G, well, it's going to be much more complicated. So certainly there's pt, that has to be the first coefficient. I mean, it is here too, it's just that p is 0 because we're in FP bar. And then, I don't know, who knows what coefficient of t squared, who knows what coefficient of t cubed. It's rather complicated. All you know a priori is that this modulo I is this. So those question marks, maybe this one belongs to I, but you don't know what it is. In any case, it's sort of complicated. But when you pass to the world of formal vector spaces, everything that was nice about working in characteristic P suddenly still works in characteristic 0. And that's one of their main advantages. Formal vector spaces seem to have the nice properties of working in characteristic P, except they live in characteristic 0. So here's the thing. If I have a test object R, I've got multiplication by P in G as a map from G tilde of R to G tilde of R. And by that kind of crystallinity lemma, this is the same as G naught of R modulo I. And I can do the same thing over here. And then this vertical map, of course, is multiplication by P once again, except this time it's in G0. Which is amazing because multiplication by P in G0 is so simple, and it seems like we've forgotten all of these coefficients. They just don't matter anymore. So after I kind of forget the QP vector space structure, this is just nil flat R mod I. This is nil flat R mod I. And this map is, well, this is sort of tautological. Multiplication by P and T is just x goes to x to the P to the H. And now I like undo that crystallinity lemma. And good. And here's this. Flat of R. Okay. So these are isomorphic, and therefore this has to have some nice expression. But this is a very easy exercise. So raising to the power of P to the H here corresponds to guess what over here? Raising to the power of P to the H. That doesn't change. Okay, so this map is also x goes to x to the P to the H. And this is a massive improvement because multiplication by P over here was complicated. Multiplication by P over here is very simple. So it's sort of, with respect to this kind of coordinate, multiplication by P is very, very easy thing to work with. Okay, so that's one very nice aspect of formal linear algebra. Multiplication by P is very easy. Here's another aspect of formal linear algebra, which is that you expect exterior powers and determinants to exist. Okay. So somehow, if G is a p-divisible formal group, G tilde is a formal QP vector space, and this next bit is going to explain, like, is there something like wedge I of G tilde? So this turns out to be important for our present situation. So do that as next. So it turns out there's a pretty nice theory of them, but I just want to explain how it works in one example. So let's just assume G0 is a very specific sort of p-divisible formal group. It's just going to be the formal group attached to E0. And let's say that this guy is supersingular. So we get some height 2 formal group, E0. G0, that's the formal group. And so as I mentioned, I think a couple lectures ago, this thing has a Weil pairing on it. It's like its p torsion is self-dual. So the Weil pairing gives us something like this. So I think I called it delta n. So you've got G naught p to the n cross G naught p to the n. This is a morphism of group schemes to mu p to the n. But mu p to the n is just the p to the n torsion inside of Gn hat. Okay, so we've got this alternating map. I mean, it's ZP alternating. Right. I mean, in fact, it works. Yeah. Okay. So this is all going on over FP bar for the moment. Only over FP bar. The Weil pairing exists. But what I'm going to do is sort of promote this to something on the level of QP vector spaces, formal QP vector spaces. So this is going to be G tilde cross G tilde to the formal group associated to GM hat. So unfortunately, there's a lot of decoration involved there. GM hat tilde. Okay. And this is going to be over the ring of Witt vectors, W. All right, so I better explain how this works, and this might be the most, well, it's not terrible, but involves concentrating a little bit on all these objects. So let me just explain. So let's say R is, right, I forgot to explain that this is supposed to be QP alternating, right? QP alternating. Right. So somehow GM, this formal vector space is the second exterior power of this one. That's how it should work. Okay. So for a test object R in attic FP bar, when you take R and mod out by its ideal of definition, well, you're modding out by something big and open, and that's discrete. When you mod out by something open, it's something discrete. And when I look at G0 of R mod J, so that's the underlying set of G0 of anything is the topologically nilpotent elements, but it's discrete. So if I say topologically nilpotent, that's just nilpotent. Like there's some finite power, you raise it to, you get 0. And multiplication by P on this guy is just like raising to the power of P squared. So that means that this is a torsion group. It's P power torsion. P power torsion. Okay. So for every element in here, there's some power of P, you can multiply it by it to get 0. All right. So that means the following thing. If let's say we've got some element in the formal vector space. So if this thing is in G naught tilde of R mod J, so right, multiplication by P brings this to this and this to this and so forth. But that means that there exists some n such that P to the n of x0 equals 0. So P to the n, if I call this thing x, so P to the n x, it begins with a 0. So the first coordinate is 0, the second coordinate is P torsion, and so forth. So this guy lives not in the big formal vector space, but in the much smaller Tate module. It lives in the inverse limit of G naught P to the n R mod J. Okay. So for every element in here, we multiplied it by some power of P to the n, and now it lives in this thing. And this thing looks like something that we know has a Ve pairing on it. Okay. So the upshot of this discussion is that, okay, let's look at that Tate module. Leave a little space. This includes into G tilde of R mod J, right? I mean, this is just like the subspace of this of elements where the first coordinate is 0. And what we've just shown is that when you invert P, you get an isomorphism. That's what this shows. Every element in here, if you multiply it by a large enough power of P, it lands in this submodule, and therefore this is an isomorphism. Okay, good. And what's nice about this is that this group scheme is autodual. This has a Ve pairing. And therefore, so does this. On the other hand, again, appealing once again to the crystallinity property, this is just G tilde of R. So G tilde of R has a Ve pairing as well. Okay, great. And let me just go over here. So, oops. So this is wonderful. So this actually means, I hope I'm not skipping over too many details here, but let's suppose that G, do I have some lift yet? Ah, right. So let's say that G is a lift of G0 to W. The Witt vectors. Okay. So now I can talk about the Ve pairing. So G tilde of R, oh, right. Now R is a test object for W. So say R is an attic W. Okay. So G tilde of R, G tilde of R, that's the same as G naught tilde of R mod P, G naught R mod P. Now we're in this situation where like the role of R is now being played by R mod P. So here. And this has a V pairing, so I can talk about this mapping into GM hat tilde of R mod P, which is the same as GM hat tilde of R. Okay, good. Crystallinity property everywhere, at every step. Okay. So great. So I'm going to call this whole thing delta. And so what I just did is I just defined, no, it's not, it's Roman. A QP alternating map like so. And, okay, QP alternating. And because G tilde is a formal vector space, this is representable, once I forget the vector space structure, to nil flat cross nil flat. Oh, so by the way, this is all going on over W. And if I look at this, this is telling me that if I have two sections here, x comma y. All right, so little grain of salt when I write x comma y. What do I mean? X is a section of nil flat, but x isn't just x. It comes along with an x to the 1 over p, an x to the 1 over p squared. It comes along with privileged p power roots for every n. And this maps to, well, I'll call it delta xy. Okay. So great. So delta of xy has to be a special element of W. Well, yeah, sure. W of, yeah, double brackets x 1 over p infinity, y p infinity. Okay. And it itself, since it lands in here, it itself has to come equipped with pth roots for every power of p. Yeah. And this power series is very, very strange. I mean, all right, so now I've shown that this determinant map exists, and from before, remember that, if you don't mind me doing this kind of thing, that multiplication by p inside of G tilde corresponded in the nil flat to raising to the p to the h. And applying that here, I mean, it's supposed to be QP alternating. So if I multiply one of these factors by p, the p should pull out. But what does that mean? It means that delta of x to the p squared y has to equal. I mean, if you believe all this functoriality, then you have to accept that this works. So this is multiplication by p inside of G, whereas this sort of thing is like multiplication by G inside of GM. It's like raising to the power of p, with the sort of weird caveat that I've actually placed the origin at 1 here rather than at the usual 0, but whatever. You could, there's a version of it where you don't do that, but okay. I like this version. Okay. So without saying what this is, it just has to exist. So tomorrow, my group will present an explicit formula for delta of xy. Okay. It's very interesting that it should exist. Oh, and by the way, delta of yx, as it must, should equal delta of xy to the minus 1. It has to be alternating because it's a determinant. Okay. Okay, great. All right, I haven't said a thing yet about modular curves, but it says, I mean, it just appears to me that you really should get all of your functors and all of your properties down pat, and then you let them do the work for you. So this is what we're going to do. So I'm going to, this is kind of the last section of the talk, and it's the deformation ring at infinite level. I'm going to take things to the infinite level. So as usual, I let yn be the following modular curve. So y of, so gamma 1 of n is some auxiliary prime to p integer, at least 5, and I consider this over W as a scheme over W. So this is the Katz-Maser model over W. And this guy is arranged in a tower. So I've got y1 over here, or y0, y1, and so forth. We also have, we can do this thing where we pick, let me write y2. I also did this thing, starting from the first lecture, these things are not geometrically connected, so let me just do this. So if I pick a pth root of unity, I can pick out that connected component. If I pick out a p squared root of unity, whose pth power is this, then I get a component there and so forth. So let me just do that. Let me pick components at each level of the modular curve. And so yn zeta p to the n, it's this regular scheme over the ring W adjoin up p to the nth root of unity. Okay, so great. Let me also make some more notation. So usually what I do is I pick a point on the special fiber. So let me just do this. So x0, x1, x2. Here xi is supposed to represent an element of this scheme valued in fp bar. So it's a point on the special fiber, and I assume it is a supersingular point. So x0 corresponds to some elliptic curve E0 over fp bar, and this is assumed to be supersingular. And let me let G0 be its associated formal group. This is a p-divisible formal group of height 2 over fp bar. And so I can basically just assume that it's a formal p-divisible group from the previous slide together with its Weil pairing. Okay, so those are the schemes and these are some points on them. Now the local rings. So let's let, for each n, let me let an be the completed local ring, O hat, of the scheme yn at the point xn. And I can also play this game once again with zetas, so I can even put a decoration there and a decoration there to give me the the completed local rings at the supersingular points on these connected components. And so just remember that A0, so A0 maps to A1, they're local rings and they're going to go in the other directions as the morphisms between the schemes. A0 is isomorphic to W double brackets T. It was very simple because we had good reduction when P doesn't divide the level, but as you go up this tower, you don't know what these things are. They become very mysterious. The notation continues. I offer my apologies, but there's a lot of notation. So the thing to consider, and basically the main object of the whole course, was to study this local ring. It's the forward limit of the ANs, but that's not complete, so I'd better complete it. And of course, I can do the same thing with this. Call that thing A zeta. So zeta is going to stand for the compatible family of p power roots of unity, and A zeta will be this thing. And notice that this thing contains, AN zeta p to the n is an algebra over this guy, so this had better contain the same thing you get when you do this. And that's just, W adjoin P infinity hat. Remember this thing? This thing is non-notarian, so you have to complete it. Okay, so this thing I'll just call OK. Right? K will be the completion of the maximal abelian extension of QP, right? By the Kronecker-Weber theorem, that's the same thing. Okay. All right, so this is the object we want to describe. It's a local OK algebra. Okay. Right, good. And one thing, okay, so when we added these level structures, right. So here's the thing. So A0, is the deformation ring of the formal group G0. And then this means that there's going to be a universal deformation G univ over A0. And then when we passed, right, that's what A0 was. That was the whole point of me presenting the Serre-Tate theorem, was to give you an interpretation of A0 this way. It was the deformation ring of G0. It governs deformations of G0 to characteristic 0. So over it, there's a universal deformation ring. And then over these other local rings, these ANs, what we discovered last time, I mean, this is sort of, I wrote this down last time, that there are universal parameters, xn and yn, inside of G univ. And to get them, you have to pass to one of these rings, an, zeta p to the n. A lot of setup. But as I said, kind of the functoriality will just kind of do all of the work for us. All right. Oh, and I suppose the last thing that I have to say is that as far as setup goes, before I kind of get to work, is that delta n of xn, yn is a zeta to the p to the n. That was the whole point of belonging to this ring. Describes the part of the modular curve where the Weil pairing of the level structure just gives you zeta to the p to the n. Right, so I did say this last time. Okay. All right, great. All right, so what we get is that, oh, wonderful. All right, so now I do the following weird thing. I go ahead and I let G over W be an arbitrary lift of G0 to W haphazardly. Okay. Great. Now, G universal is a lift of G0 to A, and A to A0, and A0 is something complicated, but W is something simple, and I'm just going to lift G0 to G in whatever way I like. Then, when I take G and I base extend it to A0, and G univ, these have the following things in common. So they are both lifts of G0 to A0. They're both defined over A0. But when you mod out by the maximal ideal of A0, here you get G0, and here you also get G0. Because I said that G was a lift of G0. They're both lifts of G0. Okay. Thus, when I pass to formal vector spaces, they're the same. Oh, let me just write that. Great. And that was the very key property. If you have two lifts of a common p-divisible formal group, their universal covers are isomorphic. They're even canonically isomorphic. Great. Now let me use some of this structure that I've got. At each level, I've got a pair of torsion points. Oh, I didn't write that they were torsion points. So this is true, but better yet, you get that they're torsion points. So the x's and y's give two elements in the inverse limit, I mean, essentially the Tate module of G univ p to the n of A zeta. They all live in A zeta. All the an zeta p to the n's, that's a subring of A zeta. So of course they all live in a common ring. It's just a very, very large ring. This inverse limit is just a subgroup of G tilde univ of A zeta. Right? I mean, this is just really the subgroup of this consisting of sequences where the first coordinate is 0. One is inside of the other. But by this previous observation, this is the same as G tilde, where G is the arbitrary lift. And this is isomorphic, of course, to nil flat of A zeta. So I have two elements in nil flat of A zeta. That is, I have x, x1 over p, and so forth, and they all live in A zeta. And y, y1 over p, and so forth, and they live in A zeta. And furthermore, by this Weil pairing thing, I know that delta of xy to the 1 over p to the r equals zeta to the p to the r by this, where delta is that power series that we'll tell you about tomorrow. Okay. Oh, okay. Well, in one more minute, so I'm very close to being done. I've got these two parameters inside of A zeta. They satisfy that relation, and therefore we've got a continuous map like so. Maps to A zeta. And then the theorem, which I can't prove in 2 minutes, is that they happen to be isomorphic. So this is a complete description of the local ring of the modular curve at infinite level. And this is completely explicit. All right, so I'm just going to sign off by saying that this work was heavily influenced. Like, I figured that something like this might be possible by reading the work of Farg on the Lubin-Tate Tower. The idea for G tilde is really originally due to faultings, and the properties of formal vector spaces were appear in a preprint of Farg and Fontaine. They even use the word espace vectoriel formel. And then the last thing I should really say is that if you liked this, this is really heading towards the direction of perfectoid spaces. And that theory, that very beautiful theory, is due to Peter Schulze. Okay. So yeah, I hope this has been interesting. I had a wonderful time. Thank you very, very much. Okay. Bye.